Welcome back. In this video, I wanted to cover just a little bit more detail in several examples of how a directional derivative works. So our first example is going to be f of xy is equal to xy squared. And we want to know about the directional derivative in the direction of the vector v equals 3, -4. Okay, so we recall that the equation for a directional derivative is def at xy is equal to e dotted with the gradient of f at xy. And we require that e be a unit vector in the direction that we're curious about. So since we want e to be a unit vector in the direction that we're curious about, this is going to wind up being v divided by the length of v. Okay. So let's start putting the pieces together that we need in order to complete this equation. The gradient of f at xy is going to be partial with respect to x here. So we're going to have y squared, because that x is going to drop off, and then the partial with respect to y in the y component. So we're going to have 2xy there. And the vector that we're going to use in this is v divided by its length. So its length is going to be 1/5 times 3 -4. And as I've said previously, I like to leave the fractions out front so that way they're not getting tangled up too much when we start distributing things or multiplying things later. So let's plug these things in. Our directional derivative in the direction of e of f xy is equal to 1/5 3 -4 dotted with our gradient y squared to xy. So that's going to be 1/5 times 3 times y squared minus 4 times 2xy. We can kind of simplify that just a little bit, and you're going to get 1/5 3y squared minus 8xy. And that's really about all we can do with that one. Let's do another example. In this example, we'll have three components in our three variables in our formula, or in our function here. We're going to have g of x, y, z is equal to xy squared z cubed. And the vector that we're going to want to look at this time for our directional derivative is going to be I hat minus 2j hat plus 2k hat. The formula that we're going to use is exactly the same. So directional derivative of g of x, y, z is equal to e dotted with the gradient of g at x, y, z. And this vector here is just going to be a unit vector in the direction of v, so that's just v divided by its length. So now all we have to do is compute this and the gradient of g and then plug them back in, and we'll have our directional derivative. So the gradient for g at x, y, z is equal to, we'll have the partial with respect to x, so that's going to give us y squared z cubed for our first component. Next component is partial with respect to y, so we'll have 2xy z cubed. And then our third component is the partial with respect to z, so that's 3xy squared z squared. And then our vector e is equal to, we'll have 1 over the square root of 1 squared plus -2 squared plus 2 squared times the vector e itself, or v itself, so we'll have I hat minus 2j hat plus 2k hat. And I don't know, I typically like to write these out with the bracket notation, so I'm going to adjust that a little bit. This all right here is just equal to 9, so we take the square root of 9 and we get 1 over 3 times 1 -2 2 for the direction that we're going to be plugging into this equation here. Putting it all together, our directional derivative for g at xyz is equal to 1/3 1 -2 2 dotted with the gradient, which is y squared z cubed for our first component, and then I guess I'll just continue on to the next line here with our next two components, but they're all in the same vector. 2xy z cubed, and then 3xy squared z squared, just like so. So we just have to take this dot product here, and I'll move over a little bit so that way we have enough space. It'll be 1/3, and then we'll have 1 times the first component, so that's y squared z cubed, minus 2 times our second component here, so 2xyz cubed, and then plus 2 times 3xy squared z squared. Okay. So we'll just clean this up a little bit. We have 1/3 y squared z cubed minus 4xyz cubed, and then plus 6xy squared z squared, just like so. And that's pretty much all there is to that. I do want to emphasize the fact that we've seen in both this example and in the last one, notice that there are no longer components here. We are just adding terms together like this. That means that what we're going to wind up with is a scalar or just a number, which is exactly what we want out of our directional derivative. So that kind of compares a little bit with the gradients that we've been looking at that have individual components. These are just pieces that are all added together because dot product always gives a scalar. Now, the directional derivative is, you can plug a point into it. So I wanted to look at some examples where you actually plug a point into the directional derivative. So we're going to compute the directional derivative at a specific point. So we can kind of return to an example that we just worked on. F of xy equals xy squared. The directional derivative in the direction of v equals 3i hat minus 4j hat. And then we're going to do this at the point p equals 3, -2. So our general strategy here is going to be to take the directional derivative for this up here using the function and the vector, and then all we have to do at the end is plug in the point. So directional derivative in the direction of e at fxy is equal to e dotted with f at xy, right? And this is actually, I can rewrite this is 3, -4. This is exactly the same vector that we had in our first example, and it's the same function we had in our first example. So we've already found this to be 1/5 3y squared minus 8xy. And so now all we have to do to figure out what it is at the point p equals 3, -2, we just have to plug this point into this equation here. So we're taking the directional derivative at 3, -2. And so we'll have 1/5 times 3 times -2 squared minus 8 times 3 times -2. And at this point, all you got to do is simplify that down, put it in a calculator, what have you. But you are going to wind up with just having 12 at the end of this. So again, main idea here, compute the directional derivative and then plug in the point that you are given. Let's do another example. We're going to revisit g of x, y, z equal to xy squared z cubed with the vector I hat minus 2j hat plus 2k hat. And we're going to find the directional derivative of g in the direction of v, but then we're going to do this at the point p equals 3, -2, -1. So from earlier, we had said that the directional derivative for this particular function in the direction of the vector given is equal to 1/3 y squared z cubed minus 4xy z cubed, and then plus 6xy squared z squared, just like so. So all we have to do now, since we've already computed this part here, we just have to plug in the points that we've been given. So we're going to find that directional derivative at 3, -2, -1. And that's going to be equal to 1/3 times -2 squared times -1 cubed minus 4 times 3 times -2 times -1 cubed, and then plus 6 times 3 times -2 squared times -1 squared as well. You can put all of that into your calculator, and what you should get back is 44/3. So this number right here is the directional derivative of g in the direction of v equal to I hat minus 2j hat plus 2k hat at the point 3, -2, -1. And generally speaking, what this is just saying is it gives a notion of how much g points in this direction at that particular spot. So we have another style of this problem that's kind of similar, is that sometimes if you're given a function and then a particular point, we want to know how much it's changing at that point in the direction of another point. So in these next two examples, for the function given and at the point given, we are going to compute the directional derivative in the direction of another point that's been given to us, q. So in our first example here, we're going to use f of xy equals xy squared. At the point p equals 3, -2, and in the direction of q equals 4, 0. Okay, so we're looking for a directional derivative, so we're just going to go ahead and start with that equation. So the directional derivative in a particular direction, which we're going to have to determine, fxy is equal to e dotted with the gradient of fxy. Now this piece we already have. This is the vector y squared to xy. This is the one that we really need to know about. We don't know what direction we want this to point. Well, we're told that we're based at the point P and that we want it to go in the direction of Q, which means that the vector that we want to use here is probably going to be the vector that connects P to Q. But then after we find that, we have to remember that we want to normalize it because we want it to have length 1. So we'll divide by its length after we find it. So that takes care of pretty much all the pieces here, and that will then answer the question of finding the directional derivative at that point in this direction. So first we have to find PQ. PQ is equal to the vector 4 minus 3 and then 0 minus -2. So this will be the vector 1, 2. And then we just have to normalize that. And the length of this vector is √5, so it'll be 1 over √5 times 1, 2 will be the direction that we're going in. So generally speaking, our directional derivative is dfxy, 1 over √5, 1, 2, dotted with y squared 2xy. Well, this is going to be equal to 1 over √5 times y squared plus 4xy. So now we found our directional derivative, but this is kind of like at any particular point, right? This doesn't have a specific point plugged into it yet, so we're not really quite done because we're told to find the directional derivative at p equals 3, -2. We did use the point P to get the direction that it was pointing in, but now we just have to actually kind of ground it in that location, and we're going to do that by plugging in the point 3, -2, which is the part that we're really interested in. So it's going to be 1 over √5 y squared is going to be 4, and 4xy is going to be minus 4 times, well, it'll be plus -3, I guess. That's where that's going to wind up. And then times, oops, nope, that's +3, -2. There we go. Okay. So 4 minus 24 is what this piece is here. We're going to have -20 over root 5 as being our directional derivative at the point 3, -2 in the direction of q. So just to kind of recap what we've done here, we used p and q to determine the direction that we wanted this to go in. We found our generic directional derivative, but then we had to remember that we wanted to base it at the point 3, -2. So that's what got plugged in here. Let's do one more like that. Let's use g of x, y, z equals xy squared z cubed at the point p equals 3, -2, -1. And this is in the direction of q equals 3, -5, 6. Okay. So we're going to want to apply the same idea that we did last time. Start with our general equation. And this is equal to E dotted with gradients of x, y, z. And one thing that I want to emphasize that maybe I should have said in the last example is that unlike earlier, we can't just recycle what we found for this previously, because now our direction has changed, right? There's two key components to this, our vector and our function. And since we're changing the direction that we're pointing in, it means that we're changing this part right here, which means we can't just reuse what we computed for this before because a key piece of it has changed. So take care that you're not just kind of reusing what you had found earlier, because this really important part is changing. Anyway, so to be able to do this, we already have the gradient, which is y squared z cubed, and then 2xy z cubed, and then 3xy squared z squared. It's kind of tight there. But we still have to find E. Now we're basing it at the point P, and we want it to point in the direction of Q, which means that we want to use the vector PQ as part of our direction, but we always need E to be a unit vector, so we divide by the length of PQ. So let's go ahead and start with computing PQ. PQ is the vector 3 minus 3, -5 minus -2, and then 6 minus -1. So that's going to be the vector 0, -3, 7. And the length of this vector, if you square all its components, add them up, take the square root, is 1 over, or the length of it is root 58. So we have 1 over root 58 for E times 0, -3, 7. Just like so. So now we find the directional derivative x, y, z in the direction of this vector E here, which points in the direction of the point Q that we're looking at. So that's 1 over root 58, 0, -3, 7, dotted with, and I think again I'm going to run out of space, we'll have y squared z cubed. Next two components are going to go on this next line here. 2xy z cubed, and then 3xy squared z squared, just like so. So we take all of this and we'll have 1 over root 58 times, all these pieces are going to get added up. That's just going to be 0, so I'm not even going to write that down. We'll have -6xyz cubed, and then plus 21xy squared z squared. And that gives the general formula for the directional derivative in the direction of PQ. Now we want this directional derivative to be based at P, so we have to plug in that point. So 3, -2, -1. It's going to be equal to 1 over root 58 times -6 times 3 times -2 times -1 cubed, and then plus 21 times 3 times -2 squared times -1 squared. And if we add all of that up, I believe what you should wind up with is 216 divided by the square root of 58. So yeah, that's pretty much all there is to doing these kinds of problems. Again, use the base point and then the direction that you want to point in to get the vector that you'll actually plug into here. And then just don't forget to plug in the point that you're basing it at, and again at the end. So, but that's pretty much all there is on directional derivatives. Fairly straightforward as long as you make sure to start with this equation right here and then just build from there.